right, so first of all, there's just all kinds of memes. So now that you're smart, can you see what it says up there? On my screen, it says I'm sharing the screen, so I can't read it.
Yeah, we can see it.
After your work this week, you should laugh at this. You're all laughing, right? I know you're muted, so I can't hear you, but you're all laughing. Yeah, it's pretty funny. Yeah. How about this one?
That's definitely not how I think, though.
That's a good one.
And for like serious purpose here, here is a laundry list of Taylor polynomials. And here's the reality. And I want this message to be heard well going forward today. Once you've created a Taylor polynomial, say for e to the x, there it is, or sine of x or cosine of x, you don't go do those again. Once you have them, they're done. You just use them. I'll show you that today. But because you're in a math class, we do want you to kind of know where they're coming from, how they're developed, and then focusing on what we're using them for. So I hope today you'll get a better picture of what it is we're doing. And just, I bought you all t-shirts. They're coming in the mail. Don't y'all want a Taylor series derivation t-shirt to wear proudly?
You did
It's
not.
pretty awesome. Like, look at that. For sine of x, the one that I did for you on the video. How nice was that? Is he not here?
Not here. No, he's not.
All right. Well, I just going through what you submitted, and honestly, this wasn't like his is the best or anything like that, but I just wanted you to see that from afar. Don't look at a line, don't look at a particular letter or a number on this page. Just look at it like sit back and gaze. This is what it looks like. Now, make his exact process, but just from afar, you can see, I hope, this process, this development of a Taylor polynomial. Which one is this? This is cosine. The idea is, can we ultimately create an infinitely long, hey, pause right there. Where's Zach? Zach, since January, you've been the infinitely many, infinitesimally thin guy, right? Now we're doing infinitely many, but infinitely many terms of a polynomial. Can you imagine taking this plus this plus this plus this plus this? You lost a plus in there. Plus this plus this plus this plus this forever. Express that idea forever. What we have is to express a here's the term for the day, transcendental function. The transcendental function is like sines and all the trig functions, exponential functions, logarithmic functions. Those are all classified as transcendental. Then you have algebraic functions, polynomials, for example. I hope you saw, I'll get to that later, but we have reasons why it's helpful and necessary to be able to represent transcendental functions like cosine of x as a polynomial function like this. Add to one. Moz isn't here. Is he really not here, Moz? He does have one error here. You notice it's 2, 4, 6, 8. Who do we appreciate? Right there. Can you see my pointy?
You should have a 0 factorial right there.
0, 2, 4, 6. It was all the even degree, all the even derivative or zeroth derivative. So it should be a 0 factorial. And this is a crazy thing, you guys. 0 factorial. Now, hold on. 4 factorial means 4 times 3 times 2 times 1. Or 5 factorial means 5 times 4 times 2 times 1. And over the years, of math development, the symbology for that, they started using the exclamation point. So you would have a 5 factorial or a 3 factorial or a 6 factorial. And of course, anytime you write it, like when Maz wrote it right here, 6 factorial, you should say 6! Blew up there. Colton, you all right, man? We can't hear you. It's 6 factorial. But what about 0 factorial? Let me change it because I'm not happy that that's the one right there. That should be a 0 factorial.
When you heard that.
0 factorial. What does that mean? How do you have like 5, 4, 3, 2, 1? How do you have 0 factorial? Well, guess what? It's defined to be 1. We do that in math sometimes. By definition, 0 factorial is 1. And that definition isn't random, like, hey, let's just randomly make something up. No, it was because in this situation and every other one that it comes up, if we make 0 factorial 1, and like things like this work out well. So it's a great definition, strategic, well thought out. Also, I'm going to ask you to watch a video next week as part of your assignment, and you see it's Eddie Wu. I don't know if you know Eddie Wu, but Eddie Wu is a pretty popular online video math guy from Australia, and he does a quick little demonstration of why 0 factorial equals 1 makes sense. I'm going to let him teach it to you. All right, so there it is.
Hey,
Cosine, big process. Yeah.
with 0 factorial and 1 factorial, they're both equal to 1. So I don't understand what's wrong with using just 1 factorial or what Maz did. He did 1 over 1 factorial. It's the same exact thing.
It is the same thing like right here. The problem is more when you get into his formula here. So when n is 0, 2 times 0 is 0, 0 factorial. So in his formula, the 0th term would be 0 factorial down there, not 1, as he has. So it's not so much that it's wrong as much as there's kind of a mismatch then in his infinite Taylor series.
Okay, gotcha. Thanks.
Yeah, good. I'm glad you said that. That's a very good point. Yeah, so we do it. And then what I wanted to do is just, I know I did this in the video, but I want to make sure you're kind of getting the bigger picture is Desmos is such a great tool. And some of you that have emailed me recently, I've said, hey, put it in Desmos and see. Here's what I mean. So I've defined the function f of x to be the cosine of x. Let me turn this off for a minute. And I hope you all can look at this and go, yep, that's the cosine curve. It makes sense. I'm familiar with that. If not, email me because I have a video. I have a video about sines and cosines. I would love to have you watch to know why this graph makes sense. Then, don't look here. That's something else. But here is Maz's infinite Taylor series that I just put into Desmos. By the way, to get Desmos to make sigma, you just type SUM, like summation, and it pops up the sigma summation notation. And then n equals 0. The problem with Desmos is it doesn't understand infinity. Like it's not going to just run this thing to infinity. So I put a slider. I didn't put the slider. I put A. And then Desmos said, do you want to make a slider for A? And then we can make A go to infinity or 50. So you'll see it happen here. There's the Taylor polynomial definition that you all did, I think. But now watch, here it comes. As A increases, this polynomial behaves more and more and more like a cosine curve. And I don't know, eventually, because you guys, even on Desmos, when it gets into like 37, Desmos right now is very quickly computing 1 divided by 2 times 37 factorial. So it's doing a 74 factorial, x to the 74th power. So even Desmos gets a little glitchy when n gets too big. I don't remember. I think maybe I stopped at 50 just to avoid some of the glitch. But look, even now it's a little slow. But I hope you get the idea. You get the sense that indeed this Taylor polynomial, or this series, I should say, does represent the cosine of x well. And even though these aren't the right ones, I think these are for sine. But if you typed in the actual terms that you saw on Maz's paper, you would also see the same kind of convergence occurring. Now, here's the calculator part. Are you ready? What does a calculator know? Like, go old school here. Suppose I grabbed my good old TI-84 and I typed in the cosine of 2 radians. It's going to output negative 0.41614. I know that because f of x is the cosine of x. I typed in f of 2. So Desmos calculated this for me. Thank you very much. Now here's the question. How does a calculator know that the cosine of 2 radians should be negative 0.416? Now, if we're in the classroom, you guys know I've been doing this for a long, long time. And so we would have this time. I'd, hey, talk to your partner about this. And you guys would come up with all kinds of things like somehow inside this calculator is a database. And the user types in cosine of 2, and the calculator searches its database for 2 cosine and spits out the answer. And that's a great theory, but here's the problem with that. How many things relative to the cosine of an angle, how many things could a user type in? Cosine of 2, cosine of 1, cosine of 1.8, cosine of 2.7, cosine of negative 18.763. There are infinitely many things that I could type in cosine of. Therefore, the database you're talking about would have to be infinitely long. Ain't gonna happen. So what's happening inside of a calculator for it to spit out the right answer when the user types in cosine of 2? Well, one more thing you have to know about calculators. They only add. In terms of calculations like addition, subtraction, multiplication, division, basically calculators can only add. You say, well, what has a subtraction button? Sure it does. Subtraction is equivalent to adding the opposite, adding the negative. So even if you type in 8 minus 6, your calculator is not subtracting, it's adding. Well, it has a multiplication button. Yeah, but what's multiplication? Repeated addition. 3 times 5 is 3 plus 3 plus 3 plus 3 plus 3. So when you do 3 times 5, your calculator is not doing some multiplication thing, it's adding. Division is repeated subtraction, which is adding the opposite. Exponents, if you typed in 4 to the 7th power, 4 times 4 times 4 times 4 times 4 times 4, repeated multiplication, but what's multiplication? Repeated addition. It all boils down to addition. So let me go back to Maz's paper. The reason I'm saying that is this. Maz, where are you? Here you are. This cosine thing is really just addition. Now I know you're going to say, but what about the fraction? That's division. What's division? Repeated subtraction. What's subtracting? Adding the opposite. But this thing has multiplication, repeated multiplication, repeated addition. This thing has exponents, repeated multiplication, repeated addition. That's what I meant. So all in all, inside of this polynomial is all addition. So here's what happened. When Texas Instruments has to program their devices to do stuff, what they do is okay, this is like made up in my head, okay? This is all made up in my head. What they do is they go to the math department at Texas Instruments and they go, hey, mathematicians, we're going to put a cosine button on our new calculator. Can you help us? Because our calculator can only add. Can you help us so that when the user presses cosine, we actually get the right answer? So the mathematicians go to work and they generate an equivalent way to compute cosine that involves only addition. And here it is in kind of a closed form. Here's the whole thing. Summation, addition, division, addition, multiplication, addition, even factorials are multiplication, which is addition, Even if you have a subtraction, it's addition, adding the opposite. So the mathematicians go back to the Texas Instruments programmers and say, here you go, take this thing and program it into your machine. And when the users type cosine of 2, we'll actually do that, and we'll spit out the right answer. Let me show you. To kind of mimic that, what I've done here is f of 2 is the program. Desmos is also programmed. Desmos took an input of 2, stuck it into the cosine, did some addition, and came up with negative 0.41614. And the addition that it did was this thing right here, thank you, mods. To show it to you, I've also put in g of 2. Now watch this. Look at your screen out here. You got to see this. This is marvelous. G of 2, this Taylor series right now is negative 1. Good. The cosine of 2 is not negative 1. The cosine of 2 is this. Look, 2 on this thing is like right about there. See, the cosine of 2 is supposed to be negative 0.41 whatever, but my polynomial is pumping out a cosine of 2 as being negative 1 because I don't have enough terms yet. I only have the one term, a equals 1. I have 2 terms of this. I have 0 and 1. That's all I got. So to get better, we need more terms. How about 3? Is that better? Better, but not good enough. How about 41614? 6, 8, 3, 6. Oh, 3, 6, 3, 9. Ah, keep going. And now, even with just 17 terms, this thing that only adds is now pumping out the same answer that we need for the cosine of 2. Guys, I'm telling you all that, and please do not think that I could actually go into here and program this calculator. I can't. I took basic programming in 1983. Things have changed. You can Google it though. Seriously, if you're interested in programming, Google the how does a calculator do sines and cosines and logarithms, whatever, and you'll, at least for me, the first 3 sentences, something Taylor series, I'm like, yes! And then pretty soon it's into coding and I lose them. But my job, Calculus 2 class, is to help you potential coders, programmers, to see how you could apply this mathematical knowledge to your programming knowledge and run with it.